Morning, Kevin. Put down as Audency here. Probably when you sent your name in, as it were, then or you were asked to talk, you were in Audency, but now you're in Copenhagen, excuse me, Aarhus.
Yeah.
Isn't that right?
Yeah.
Yeah. Okay, here.
Okay, so Anya gave me this title.
Sorry.
And as you will hear, most of the data which I'm going to present is definitely on prebiotic molecules, since it's mainly on molecular hydrogen formation on surfaces. But I'll end up by telling how we plan to use these same techniques to study the formation of more complex molecules on the surfaces as well. So, as David said, I'm Julie Warnica, and at the bottom there in red you can see some of the other people who have contributed to this book. So, as most of you probably know, 123 different molecules have been detected in the interstellar medium or in meteorites, and their complexity range up to molecules containing 13 atoms. Now, for a number of these molecules, efficient gas phase routes, formation routes are well known, whereas for other of these molecules, and also for some of the very important of these molecules, no such efficient gas phase routes for formation are known, and it's been suggested that these molecules are then formed on the surface of interstellar dust grains. And of the most important molecules, of course, is molecular hydrogen, which is the most abundant molecule in the interstellar medium, but also molecules like water molecules in the regions where the abundances are high, and methanol are believed to be formed on the surface of dust grains. So the dust grains are believed to be mainly carbonaceous grains or silicates, and in the dense interstellar clouds, these grains are covered by icy mantles, which are mainly water ice, but could also be CO, CO2 ice, or other species, methanol ice, etc. As you can see on these two pictures, which I should say Anya has given me, the morphologies differ a lot. In one case, we have a graphitic-like closed-off surface, and in the other case, we have a very porous structure. Okay, so when we went into this game a little less than 3 years ago, it had already been proven that you could actually form molecular hydrogen on some surfaces of interstellar relevance. So what we went in to try to figure out was first, what are the efficiencies for molecular hydrogen formation on mainly water ice surfaces, but also to see if we could answer what the energy, what happens to the 4.5 eV of energy, which is released when you form a hydrogen molecule on a grain surface. Does it go into kinetic energy of the formed molecule? Does it go into molecular excitation, or does it go into grain heating? How the energy is deposited will hugely influence the thermal evolution of the interstellar clouds, and thereby also influence the lifetime of these clouds. So the setup in a schematic version, we have a copper substrate which we can cool down to temperatures below 8 Kelvin. On top of this the substrate, we are then growing our amorphous solid water film, our interstellar analog. It's believed that such amorphous solid water, or amorphous water ice, is a good analog of the ice mantles on the interstellar grains in the dense interstellar clouds. So then onto this, what time we keep our substrate at when we are growing this amorphous solid water ice, we can decide whether it's going to be a porous ice film or whether it's going to be a dense, non-porous ice film, or even to crystalline. And on top of this, we then use our hydrogen atoms, and we're using both H and D atoms, deuterium atoms, because that way we detect whether we are forming Hd on the surface, and then we're pretty sure that the molecules we are detecting were really formed on the surface and were not just residual H2 molecules or D2 molecules, which were not probably dissociated in our beams. So we have our two beams coming in. Once we've deployed the atoms on gas, we can then heat up the entire sample by bombardment with electrons. And then we have a protocol mass spectrometer, which is a differential pump, which we can right up to the sample surface, 2 millimeters from the surface. And then we can look, do we, when we heat the sample, or during the dose, do we dissolve any hydrogen in this case. So the schematics looks quite simple, but in reality, both things are more complicated. So you can see this is the main vacuum chamber here, and it's all done on done-pipe vacuum. And here we have our atomic beams, the dissociation regions, and then also differential pumps. The chamber, our sample is in the center here, cooled by helium. And yeah, this is a movable mass spec. So how does the data look when you get out of this science experiment? What you see here is a very well type of data, and the science is such a programmed absorption data. And you focus first on the black trace here, what you see is that at low surface temperature around 17 Kelvin, something like this, there's no distortion or no release of molecular hydrogen from the surface. Then when we get to around temperatures, we begin to see release, production, or at least release of molecular hydrogen. As with high temperatures, this production increases. At that point, we begin to deplete the surface, so there's no more atoms left, no more molecules left, the discussion down there. The traces of the color that just what we see goes with both atomic hydrogen and atomic deuterium. You can see we only get a big signal in the case when we have both two species present. Okay. So now we can of course vary the ice substrate we're working on. We can change its thickness and see how it affects our total signal. We can also change the temperature, which we can heat up the ice instead of lower its structures. In the case of the green curve here, we have an ideal ice, so this is gold at 10 Kelvin and we heat to about 10 Kelvin. So we have a very hot structure. When we heat up to 60 Kelvin or 100 Kelvin, instead of the or we can have the ice for a short time, and we get a lot of molecules from the salt, and we take it also to the temperature. We can make a time of flight measurement, and then we get the kinetic energy of the formed molecules. And we've done this for molecular hydrogen, or HD, formed on this very low temperature ice, the porous amorphous solid water. And what we see is that it comes off very slowly, and the data are the thin black line here, whereas the thick black line is what we would expect if the molecules were coming off at a thermal Maxwell-Boltzmann distribution at 45 pounds, which is the temperature of the sample where we want it to go. So the Hg formed on these very porous amorphous solid water comes out completely thermalized to the sample. So no energy goes into kinetic energy in this case. Now, how can we explain this? Based on putting all this information I've shown you and some more together, we get actually a physical, and in this case a bit of a cartoon picture of how molecular hydrogen is formed in these structures. So even at 8 Kelvin, the hydrogen and deuterium atoms are actually mobile on the surface. So what you see here is like cut through this very amorphous solid water ice. So the black parts here is supposed to be water molecules, the white parts are the pores. So even at 8 Kelvin, atoms will be mobile on these inner pore surfaces. The typical size of the pores is 2 nanometers. So the particles will be able to move around inside these pores. Eventually they'll meet each other, they'll combine. When they recombine, they might go off from the surface here with some of the kinetic energy. They might come off internally excited, but then they'll bounce around in this porous structure, and eventually they'll lose all that kinetic energy and get reabsorbed somewhere else in these pores. Now, if this takes place in a cloud in the interstellar medium with a temperature between 10 and 15 Kelvin, then probably they'll sit around in this spot for a few weeks before they get absorbed thermally, or the energy barrier, and then they'll move around a bit more until they get reabsorbed again, and they'll do this for a typical ice thickness of 200 monolayers. They'll do this for a few times, and then after a year or so, they'll manage to make their way to the outer surface and so. When we do our experiments, as you saw before, we don't have the patience to wait for that. We don't have the money to spend in cooling us sample with liquid hydrogen for a year. So we instead do this heating to speed up the process either by electrical bombardment or by heating. So, but we can extract from these measurements what the energy boundary is for the desorption, and we can see that even at the low temperatures in the interstellar, this process could be quite an efficient process. We have derived the efficiencies, and the graphs here are the efficiencies for formation of, in this case, B2 in the amorphous solid water, porous amorphous solid water ice. And what we're really seeing is the part that's retained, getting trapped in these pores and then dissolving as we leave the sample. And this efficiency is quite high, it's 35%. And this means that each time an hydrogen atom, collides with an interstellar grain surface coated with this porous amorphous solid water, then it will have a chance of 35% of sticking to the surface, moving around, finding a partner, recombining, and getting trapped in the ice. We've also done the same measurement for the non-porous surface, so the amidal surface, and here the probability is much lower, it's like 5%, something like that. This does not necessarily mean that you cannot form molecular hydrogen on these surfaces. It only means that if you form it on these surfaces, it will be inhabited promptly, and the formed molecule will be promptly released with presumably most of the energy going into kinetic energy and internal energy. I should just right there in this picture, since the molecule will be sitting around on the pore walls for up to a year, or even as long as it stays there for more than, or for a time scale of milliseconds, all internal excitation will also be coupled into the ice structure and will be lost. So in the case of the porous structures, the porous ice structures, all energy is eventually deposited into the grain. So this means you could have different things going on. You could have local restructuring of the ice. You could also maybe thermally catalyze other chemical reactions on the grain, or you could even dissolve other species from the grain due to the large energy or amount of energy which you're releasing locally. Okay, good. So we've also studied detumination on graphite, and these are quite recent experiments. And here you can see the same kind of experiment that I showed you. The first thing that we're heating the sample up with a slow linear ramp. And you see that you get a completely different temperature range. So here this option starts at around 400 Kelvin, and even higher energies. That even to get in the state on graphite, get the atoms into the state on graphite, you need high energy atoms. So these results would not be relevant for the dense interstellar clouds, but instead be relevant for photodissociation regions. So here we see we can also form D2 on graphite. We've done the same type of laser absorption measurement as I showed you before, but here instead of dissolving or cutting off in a time scale of the red and the blue are essentially the same in this case. Instead of coming off on a time scale of 200 microseconds, we are now seeing molecules coming off at a time scale of 20 microseconds. So this means they're coming out quite hydrothermal. They're coming out at energies which are 100 times bigger, so corresponding to several thousands of Kelvin. So depending on what the substrate is, the mechanisms for molecular hydrogen formation varies quite a lot, and also the energy dissipation in this process varies quite a lot. Our next goal for this system is to directly measure the internal vibrational state of the D2 coming off the graphite surfaces. So, as I said before, these transmissions would be relevant for H2 formation in photodissociation regions where an overpopulation is observed in vehicles for. This might be due to pumping by the formation process, and maybe our data here in this system will be able to shed some light on whether this is possible or not. So I move on to the outlook. This was molecular hydrogen, more simple molecule. Can we form more complex molecules on these surfaces as well? One of the first things we'll be looking at is the formation of water from atomic hydrogen and oxygen, the formation of ethanol, and also hydrogenation reactions of other molecules. A lot of the very complicated, or the molecules containing a lot of atoms which have been observed in the interstellar medium are highly hydrogenated species, and it would be quite probable that some of this hydrogenation could happen efficiently on the dust grain surfaces where the concentrations are higher than in the gas phase. We will also further investigate to what extent the grain surface morphology, the porosity, influences the dynamics of the formation process. So we've seen it influences the formation process of molecular hydrogen by quite a lot. Will this also be true for the larger, more complex molecules? At some point, of course, the molecules will be so large that they will not really be able to diffuse into the porous structure. Finally, we can also go the other way around and look at to what extent the formation process influences grain surface morphology. I started out by saying that we've been working mainly on the surface of amorphous solid water, because this is believed to be a good analog of the ice mantle in the interstellar medium. But this is really only a partial truth, because it's known that in the dense clouds, the water is really not condensing out from the gas phase. It's formed in situ on the surface from atomic oxygen and atomic hydrogen. And one of the things I'm proposing to do in the coming time is to use STM to actually go in and look whether the structure which you get of the water, if you form it on the surface, is different from the structures which you get when you are depositing the water as molecules. And finally, as I said before, if you are making a molecule like molecular hydrogen on the surface, you might deposit a whole lot of energy into the surface, which would cause local restructuring, it would cause desorption of other species, which is referred to as chemisputtering, and it could also lead to diffusion of other and thermally catalyze other reactions on the surface. Finally, another thing which I plan to look at is to see whether more complex molecules formed on these grains will be able to self-assemble. Self-assembly has been observed on a lot of other, on a lot of metal surfaces and a lot of liquid covered surfaces using STM. And what we plan to do is, or supposed to do, is to see whether molecules, complex molecules, will actually also be able to self-assemble under interstellar conditions, so at very low temperatures, very low pressures. Thank you for your attention.
Thank you very much, Stu. Some questions, please.
So some of my astrophysics friends, they've said that when you have a condensing cloud around a star, at the very beginning of planet formation, it doesn't need to be as cold as you are assuming there. So maybe you could, instead of saying that you were simulating one of these clouds, you could simulate one of the some of the early grain formation in the planet.
Yes.
Is that, I mean, some astrophysicists here that can comment on that?
I guess the thing is that in most of the regions where you are, when you're not in the dense interstellar clouds, you have UV radiation and other kinds of radiation which will absorb water from the surfaces. So in most other regions, I guess you will mainly have the bare grains, so you mainly have the carbonaceous or the silicic grains, and not much water coverage on these ones. And if you want to simulate the formation of those, then I guess you need to go to much higher temperatures.
I think it's partly a matter of the hierarchy of questions. There's the most burning question in all of molecular astrophysics is, how is H2, commonest molecule in the universe, made in its medium? There's your answer. So, next question, how is water made? H2O, ice. So it's really, the questions you raise are very interesting ones, but you just got to do them in the order of their importance. And I think that's what Louis is doing, really, just choosing the most burning and exciting questions and going through them. There's many others which occur to one, and the one you mentioned is certainly extremely interesting too. But the question of the energy balance in clouds is that the most important internal energy source in a molecular cloud, which is condensing to make a star, is the formation of molecular hydrogen, because it uses 4.5 eV every time you make H2. So where that energy goes is vital to the energy balance, and that's why they were measuring those things. And so so the first stage of fast summation, we could put some real numbers in now, where they were just guesses, and people would just try different scenarios. Now we know which scenarios right one to put in. That's pretty important. And so it's really a question of hierarchy of problems. Than this the one you raised is a good one, certainly.
But you can also only form small stars if you get low enough temperatures.
But the mass of the starting form depends on the initial mass of the molecular cloud.
But also on how much you can cool it down.
Yeah, but that depends on the molecule. That depends on anything. No one knows about massive star formation, so I don't think I should say that all about that. Nothing's known about how massive stars form. Starting conditions or what conspires to make good stars big stars. So we know what small stars fall from.
So the H2, efficiency of the H2 combination to dependable on the materiality content, or at least the oxygen?
At least the oxygen, yes, it should, definitely. But of course, you also have two morphologies of the carbonaceous grains, so it depends on, if you get very porous structures of the carbonaceous grains, you would have the same effects on the bare grains also.
More points? I've just raised a interesting question about the metallicity. If you take the first star in the universe, are there any galaxies or anything sort of no heavy elements, and that didn't form on surfaces? Don't go and not be correctly formed, because it takes no time. But that's an interesting point. Sorry.
Yeah, I'd like to talk, but I have a question for you. I know that you're not addressing the thing because I would like to hear you think about it. One of the things that when you actually have the is there's a problem where it's difficult to explain how the boulders and so it decides that entities are how they form interpretation, because this big gap information. And one of the things that will include just that is they actually have some of the high atom number hydrocarbons, they act as a glue, so they become sticky. So one of the things that we've been hunting around, just sort of sitting in the background when he's doing that, but your instrumentation yourself, would you in principle be able to see, how TARS, using your instrument, how TARS will assemble or how it will act on the surface?
What I can say, what we could do would be more to look at whether we can make these hydrogenation reactions on these surfaces. And then also we could, to some extent, look at whether the structure evolving from that would be porous or not. And of course, if it's porous, then based on the experiments which Anja has also participated in with the Jena group, then if they're porous, then of course you have maybe a better chance at sticky behavior or something like that. But apart from that, I should say, we are not going the other way. We are asking Anja and the models they're making to tell us what are really the relevant ones to do.
Perhaps we ought to pass on, it's not very interesting, but it's not really interesting in Finland. Very late.